I am Dr. Suaibu Umaru, and I'll be presenting on descriptive statistics. Our presentation is going to be done according to the following outline. We shall see some basic definitions, talk about the different types of variables. We shall also comment on the different measures of central tendency and dispersion, and we shall finally end with the concept of the normal distribution. So at the end of this lecture, we are expected to be able to identify and know how to use the different types of variables. Also know the different types of measures, that is of central tendency and dispersion. And at the end, be familiar with the normal distribution. So statistics is that science and the art of collecting, summarizing, and analyzing data. So it consists of mainly presenting data. We have two main sections, which is descriptive statistics, that is the topic of our today's presentation, which mainly consists of summarizing and presenting the main properties of a data set. We also have the second part, which is inferential statistics, that draws conclusions and also try to establish some relationship between the variables. Here, of course, we will need to use some statistical test, and it's not part of the discussion for today. So a variable can also be defined as any property or characteristics that can vary over a period of time. It can take different values in different situations, in contrast to a constant that always has a fixed value. So we are going to be mentioning variables all along this presentation. So we have two major types of variables, that is quantitative and qualitative variables. And qualitative variables are those that are non-numeric or have no logical numerical ordering. And they also have two subtypes. That means they can be nominal or ordinal. Nominal when there is no order or in the ranking of the variables, they are not really in order. So for example, here we can talk of gender. Someone can either be male or female. For blood groups, we can either blood group A, blood group B, and so on. So it doesn't matter which one comes first. There is no one that is greater than the other. So that's why we say there is no inherent order or ranking in the appearance of the variables. A second subtype of variable here in this category is an ordinal, which of course constitute now ordered categorical data, in contrast to the nominal, where there was no order in the ranking of the variables. So we have intervals that exist between variables which are not necessarily equal. And for example, we can have pain level. We can move from mild, moderate to severe pain. For educational level, someone can move from primary, secondary, high school to the university. So at each stage, you see we are moving from a smaller to something bigger, just like we are climbing a ladder. So we have different levels, and we have a fixed order in these variables. So we talk of ordinal variables. So just to have a clear picture of what we've just mentioned, that categorical or qualitative variables can be subdivided into two. We have nominal, where there is no order between the categories, which can also, based on the different possibilities of a nominal variable, we can call it binary or dichotomous, where we just have two possible options, like someone can be either be dead or alive. There is no other option that falls in between. So this can be said to be a dichotomous. Or when we have different options, we can call it polychotomous variable. Ordinal, where there is an order between the categories, like we just saw the pain level, where we can move from mild, moderate to severe pain. So an example is looking at this paper published by the Professor Zoji and collaborators in 2021, where they were looking at hypertension in HIV and AIDS patients in Cameroon. When we look at the first column here, we see how categorical variables are being represented. For example, the age group here has been categorized into group 1, group 2, group 3, and we can also see marital status here. Someone can either be single, married, live with a partner, separated, or divorced, or the person can even be widowed. So we have different ways of presenting categorical variables. And based on the subtypes we saw, for example, this age category can be an ordinal because, of course, there is some order in the presentation of the age groups. Each time we move from a smaller to a greater or to a higher age group, and there is like a fixed difference between the age groups. But in contrast, if we move to something like marital status, you see someone can be single, married, live, living with a partner, widowed. So there is no particular order in the presentation of these possibilities. And so this can be a nominal variable. So this first column shows us the different ways by which a categorical or qualitative variable can be presented. Remember, we said it could also be binary or polycotomous based on the different options. For example, if I take this employment status, someone can either be employed or unemployed. So we see that this can be set to be dichotomous with just two possibilities. But smoking status, here we have someone never smoked, a current smoker or a former smoker. So we have more than two possibilities, and we can call it a polycotomous. So moving to the next type of variable, we can have now quantitative variables that can be measured in numbers. So they here can be discrete or continuous variable. Discrete when they can take whole numbers and cannot take decimals. That means, for example, if I say the number of this Monday research call participants today, we can either be 20, 30, 25, but we cannot be 20 and a half because there is no half person who is attending, or there is no half person. So we have whole numbers, and there we can call the number. If we take a variable to be the number of participants on this research call, we can call it a discrete variable because it only admits whole numbers. So it has distinct gaps or intervals between them. And the second type is a continuous variable that can take any number, whole number, or decimals. So still talking about the number of research participants or attendants of this call, we can also say, okay, the height of different participants of this call, we might have different values, 1.68, 1.7. So we take different possibilities, and hence this is said to be a continuous variable. So going to the same example we saw earlier on this paper, we can now look at this second column whereby the number of hypertensive patients in each that fall within the first age group. For example, they are 1,146. The number of hypertensive patients falling having their ages between 30 to 39 are 3,050. So you can clearly see that we have whole numbers here, and they are not taking any, we cannot say we have 1,146.2 persons who are aged between 18 to 29. So this is a quantitative or a numerical variable, but the subtype here is a discrete because it can't take any decimal places. It takes only whole numbers. Also, when we look at the median age of the study participant, it happened to be 42.0, or maybe the range here, which is between 18.1 to 105.8. So you see, this can instead take decimals. So it cannot just be whole numbers, it can also take decimals. And of course, this is now a continuous variable in this context. So based on what you are dealing with, you can have different types of variables, which is essential to know in order to analyze or describe your data. So the other types that we can possibly see should be the independent and the dependent variable. Although this is more of inferential statistic, we are just going to mention it, that when we want to establish the causal relationship between two events, we have to also talk of this independent and the dependent variable, whereby the independent variable is just that variable that you can that depends on the observer. That means you can manipulate control to see its effect on the outcome variable or the dependent variable. So the independent can also be called the predictor or the factor variable, and the dependent is the one being measured or observed in response to changes made in the independent variable. So a quick example here is just on this table that I extracted from a study, which was trying to evaluate the impact of obesity on the incidence of heart failure with preserved ejection fraction versus reduced ejection fraction. So you see that here the independent variable is obesity or the BMI, the waist circumference, the waist to hip ratio, all of them are the predictor variables, but the outcome now depends on whether the person with the BMI high or low BMI can have incident heart failure with preserved ejection fraction or incident heart failure with reduced ejection fraction. So in this case, our independent variable is the BMI, and the dependent or the outcome variable can be the occurrence of heart failure phenotype, be it preserved or reduced ejection fraction. So after looking at these examples of variables, let's look at the measures of central tendency. Those we can also use to represent the characteristics of a particular data set. So the measures of central tendency is that a measure, central tendency is that single value that can represent the central point of a data set. So just by just looking at data, you can have a general idea about the average, about what occurs the most, about the main characteristics of that data set using these measures of central tendency. So you have three main measures of central tendency, which include the mean, the median, and the mode. And each of these tries to find the central location using the different methods. And depending on what you are, the type of data we are dealing with, we can decide to choose one of these measures depending on which one is best suitable in our context. So the mean, also called the average, is the most common measure of central tendency that we use, and it's just gotten by taking the sum of values in a data set and dividing them by the total number of values in that data set. So for example, here we have two groups of values where we have A and B, and we are trying to get the mean by just adding the individual values and dividing by the number of values. And if we do that for example A, we see that the mean is going to be 6.5, and for example B, we are going to have 4.375. Now, one thing we have to note with the mean is that it is sensitive to what we call extreme values or outliers, and it is best used in the absence of these values, or when we have a data that is normally distributed. So to look at the effect of these extreme values or outliers, if we look at these very examples again, the first example here, we have values that involve 1, 2, 4, 5, 7. And from 7, if you look, we moved to 25. So there is a huge difference between 7 and 25. And remember, we said the measures of central tendency are trying to give us the central value of a particular data set. So by calculating the mean of the first data we have here, we will have 6.5. So we are tempted to say that, okay, the average value in this data set is 6.5. But look at how many values are up to 6 and more. That means we just have the last three values. And then we can clearly see that the value does not perfectly represent the this data. But in the second data set, we'll just replace 25 by 8, which is closer to 7. That means we have canceled the effect of the outlier or this extreme value. And when you try now to recalculate the mean, you see you have 4.4 to one decimal place. And of course, that really is more accurate and can give a summary of this data. So that represent the data well. And when using the mean, we should always check for the presence of these outliers. The second measure is the median, which also takes the middle value of an ordered set of data, and we get it depending on the nature of the data we have, whether it is odd number of variables we have or even. So in case we have an odd number, it's easier to pick just the middle value. Of course, we have one middle value. But in case we have an even number of cases, there we have to take the two middle values, add them up, and divide by 2 to have the median. So that's what we did for the values that are displayed here, whereby the face is even. So values A, set of values even. So we take the two middle values, which are 4 and 5. When we add and divide by 2, we have 4.5. And the odd number of values here, the central value is 5. So we just pick the central value. And it is equivalent to the 50th percentile, such that half of our data are above and below. So in other words, we have to say that the median split our data into 2, and it just tells us that, okay, half of the data, if it was a population, let's say we were taking the ages of persons involved here, and we'll say, okay, if the median is 20, half will be less than 20, and half of the population will be greater than 20. So the third value here is the mode, which is the value that occurs, it evaluates the value that occurs the most in a data set. And of course, based on the type of data too, you can have 1, 2, or even more than, based on the number of values that are repeating themselves. So in this data here, we see that the value that repeats itself the most is 4, that occurs 3 times. Hence, our mode here will be 4. And to always have your mode, is always good to try and be sure you organize your data in an appropriate manner. So at the end, we can say that measures of central tendency, we have 3 main measures, the mean, median, and the mode. When do we use which measure? We said that the mean can be used for symmetric distributions where we have no outliers or extreme values. The median is mainly used for skewed distributions in case you have outliers, because it is less sensitive to these outliers. And mode used for nominal categorical data, but can be used for other type of data too. Now let's move to the measures of dispersion. Remember, measures of central tendency, as the name implies, we're looking at the central values of a data, but now we are going to see how scattered or how variable a particular data can be by looking at what we call the measures of dispersion. So dispersion is a statistical term that can be used to describe the extent to which the data is scattered. It helps us understand how spread out or clustered the values in a given data set are. And the first measure we're going to look at is the range, which is just the difference between the maximum and minimum value. So in a particular data, for you to look at how it is spread or the variability, you can quickly arrange in ascending order and then take the maximum minus the minimum value. It can give you a quick snapshot of the variability involved in the data. However, you should not hear that since you are taking the maximum and the minimum value, it is certain that this range is sensitive to outliers, and we should be careful when to use it. So we move to the interquartile range. After looking at the range here, it is a representation of the middle 50% of a group of numbers. It indicates how spread the middle half of the data can be. So for you to get the interquartile range, of course, you have to also arrange your data in ascending or descending order. The median of the main data is your Q2, or we call it the second quartile, and the median here split the data into two halves. We have the lower half and the upper half. And when you get the median of the lower half, it is called the first quartile Q1. And the median of the second or the upper half is called the third quartile, which is Q3. And your interquartile range will now be the difference between Q3 and Q1. So Q3 minus Q1 here gives us the interquartile range. So this guy helps visualize the spread of the central 50% of the data, as we said, and it is not affected by extreme values or outliers. So it is a more robust measure of spread than the range. Now we see the variance, which is the average of the squared differences from the mean of a given data set. It also measures the spread of the data about the mean, and it tells us the overall variability of a given data. But this is harder to interpret due to the presence of square unit. I mean, you cannot tell us directly the exact variability of our data. And that's why we're going to see standard deviation, which measures also the spread from the mean using the variance. And it is more detailed picture of the how spread a particular data is. It is more interpretable than the variance, and it indicates typical distance of data points from the mean. So when if we take an example of the number of participants on this call today, and we calculate our mean age to be 30, for example, and then the standard deviation happens to be 10, it just simply means that our ages lie between the mean. Most of the ages lie between the mean plus 10 and the mean minus 10. So 30 minus 10 will be 20, and 30 plus 10 will be 40. So it shows that most of our ages are between 20 to 40. So plus or minus 1 standard deviation. So standard deviation tells us how spread or how variable a data is around its mean. And descriptive statistics, as we said, we have two main types of measures: central tendency and dispersion. Central tendency, we can see, we saw the mean, median, and the mode. And the measures of dispersion, we saw the range, interquartile range, standard deviation, and the variance. Let's now look at what we call the distribution of data by looking at the normal and the skewed distribution. So a normal distribution, also called the Gaussian distribution, is the type of distribution with specific properties, which state that it is symmetric about its mean, where the highest point is at the mean. And as we move away from the mean in either direction, the values are dropping, but they never reach zero. Hence, they give the normal distribution curve a bell shape. So this is what we are talking about when we talk about the normal distribution. You see the mean is the central or the highest value, and as we move from the mean, we are dropping, but we don't touch the zero line, and it is symmetric about the mean. It is bell shaped, and we are also going to see that in a normal distribution like this, the mean, the median, and the mode are equal. Yeah, so the mean and median mode are equal. We also have what we call the 68, 95, and 99.7 rule when looking at data that is normally distributed. It just simply means that in a data that is normally distributed, about 68% of the data lies within one standard deviation. One standard deviation should be plus or minus 1 from the plus or minus from the mean. That means if the standard deviation is 10, as we saw earlier, and the mean is 30, we have 30 minus 10, which is 10, which is 20, sorry, and 30 plus 10, which is 40. So that means 68% of the data will lie between uh, 20 to 40. That is plus or minus 1 standard deviation. 95% will be between plus or minus 2 standard deviations from the mean, and 99% will be between minus and plus 3 standard deviations away from the mean. So we also have what we call skewed distributions, where the data is not symmetrically distributed, and the shape is asymmetrical. So consequently, the mean, the median, and the mode are not equal. And this has extreme values or outliers. It can be moving either towards one direction, towards the right. We say it's right or positively skewed, or it can be moving towards the left or negatively skewed data. So it always, as we said, points towards a particular direction. A positively skewed data pointing to the right. For example, in a context where we have a difficult exam, only few persons score high. That means we have a lot of persons that are having low scores. So this is going to have a longer tail towards the right. And in contrast, where we have an easy exam, most students will score high, and we have the tail towards the left, and it is negatively skewed. So to demonstrate that, we have this example, this graphical representation, where we see that the frequency of the scores here, we see people with low scores. People have low scores, and only few persons have high scores. Hence, in this context, we can, when in a difficult exam, that means a lot of people are having low marks. But so we can say this is a right skewed distribution or positively skewed distribution. But in contrast, when the exam is easy, we see that many persons who tend to score high. So the mode here is towards the right, and we say this is a left skewed distribution or negatively skewed distribution. So due to the significant shift, the mean is not the best estimate of the average in a skewed distribution, and the median is the best measure of central tendency we can use in case of skewed distributions. So to conclude, we can say that descriptive statistics provide a clear snapshot of data patterns, that understanding the type of variables can significantly guide statistical analysis, that the measures of central tendency, that is mean, mode, and median, gives us the central values in a particular data set. Measures of dispersion, range, interquartile range, variance, and standard deviation quantify how spread the data is. And a normal distribution is symmetric, bell-shaped. The mean, median, and mode are the same. And there is the concept of the 68, 95, and 99.7% rule when talking about the normal distribution. So we are ending this presentation here. I will thank you very much for your kind attention.